Okay, welcome everyone to today's seminar. We're very happy to have Sunil Mukhi with us today. He's going to tell us about quasi-characters revisited. Yes, yes.
Okay, so yeah, this is basically based on this paper which came out last Friday with Arpit Das, who's a postdoc in Edinburgh. It's about quasi-characters. These are some of the papers on which this is based. The first two below are with Ramesh, who is here in the audience, and the last two are with Ashok and Samir and Dr. Ashok here. So, principle, I should probably not give too much background, but I'll try to give some anyway. So, yeah, so the basic underlying problem is the classification of rational conformal field theories in 2D. And it's been a problem that has come up on and off over the last about 40 years, starting with the seminal work of Belavin Polyakov in 84. And we know that 2D CFTs always have an infinite dimensional symmetry algebra called the Virasoro algebra. In fact, two copies. There's a number C which appears in this algebra. It is fixed for any CFT, and so it's the central charge. It's called the central charge. And to some extent, it characterizes CFTs, though as we'll see, that's exactly the problem, that just knowing C hardly tells us what CFT we have, and we need much, much more data to actually have a CFT. Now, just to mention this, though it may not come up much in the talk, it's very common to have extended chiral algebras. In fact, if we don't, and if we only have the Virasoro, then the problem is actually solved, classification problem. Because in that case, it's known that to have a rational CFT, the central charge has to be less than 1. And all the C less than 1 unitary rational CFTs were classified by Polyakov and Zamolar-Chikov. But a rational CFT in general is one with finitely many primary fields. And if we have an extended chiral algebra, that reduces the number of primary fields. So we can actually have rational CFTs. If we have some algebra besides the Virasoro algebra, which is organizing the states, so that most of them are descendants and there are a small number of primaries. So the algebra that usually or commonly arises is the Kac-Moody algebra. This is what it looks like. It's a commutator of spin 1 currents, and it has its own central element called the level of the algebra. There are also many other extensions of the Virasoro algebra that can appear and that can be responsible for making a CFT rational and having finitely many primaries. Now, there are two equivalent definitions of rational CFT, and they are equivalent due to the work of Anderson and Moore. Otherwise, you could have thought of them separately. One is what I just said, finite number of primaries under some full chiral algebra. And the other is that the central charge C and the conformal dimensions HI of the individual fields. Here I'm referring to what are called the left-moving numbers C and H. There are similarly C bar and H bar, subject to some constraints. Those are rational numbers, and each of these points is true if and only if the other one is true. So either one can be a good definition of rational CFT. This equivalence between them is a theorem due to Anderson and Moore. And just to re-emphasize, because in recent years, CFT is largely used, 2D CFT is largely used in holography with a built-in assumption that most people don't talk about, but it's there, that we have only the Virasoro algebra and we are looking for theories that are dual to only pure gravity or something. In that case, of course, the primaries would be Virasoro primaries. But here by primary in RCFT, we always mean, and this again was emphasized by these authors, that all the positive modes of all the generators, whatever they might be, should annihilate the state. That makes it primary. Yeah.
All its conformal dimensions are rational. Some finite number of that.
If you take a free compact, I guess, because otherwise it has a continuous family. So let's say you take a compact free boson.
Yeah.
No, So, yeah, exactly. So in general, I see. You're saying it's, no. So in fact,
add the extending fields. If we finite number of primaries under the full chiral.
under the full chiral algebra,
add
whatever
those
it
extended
is. No, so I think the point is that if let's take the free boson on the circle, so it has the circle has a radius r. If r squared is irrational, then the conformal dimensions are also irrational, and the theory is not rational by both definitions. Now, if r squared is rational, it could be interesting because then the conformal, even then actually it's not clear because if r squared is rational, what happens if r squared is, it is
You get a rational dimension.
You get a
So
rational
you have
dimension.
one of those vertex operators has no monodromy in all the other.
Oh,
That's good.
I said,
So extended.
all these vertex operators.
The holomorphic one, so there will be, if r squared is rational, there will be some subset of vertex operators where the holomorphic part can be taken as a separate field, which is a n comma spin n comma or dimension n comma 0 field. That will be part of the chiral algebra. And then under that, whatever is the largest chiral algebra you can make, then the theory will have fine.
So equivalence, how was it shown?
It's very interesting theory. It's based on the theory of what are called algebraic automorphisms of the plane.
Right, but the point is, suppose I start with some theory which has rational C and HR.
Yeah.
Any conceivable primary has rational HR. Right?
Yes.
Then the corresponding chiral algebra might not be the fully extended form. And if we don't know the spectrum well enough.
If you don't, that's a matter of principle. The theorem in principle says that whatever is the full chiral algebra, one may not or may not know it, but whatever it is. I mean, the point is that it's usually, I think, not that difficult to generate the full one because let's say you have r squared some value, so you get some chiral fields. At some point, actually there'll be infinitely many in principle chiral fields, but no, because if some of them are themselves composites of the others, then you don't have to worry about them. So, for example, if you have a spin 1 current, then the stress tensor itself can be the Sugawara one, then you don't have to worry about it because any primary of J will be a primary of L. So, in this way, you usually have some finite number of chiral generators.
The point is maybe you could start with some ordex of particle rational dynamics. Start taking the OP.
Exactly.
At some point, the left moving OP will vanish, but you can address the right moving. The left moving conformal dimension will vanish. The right moving one will not vanish. That will add to the right. Right? So I think it's probably the way
we can keep enumerating it and
just taking OP.
Will get everything.
Kind of proof.
For this equivalence?
Yeah.
Yeah.
That's how I was thinking.
Okay.
Unless the bootstrap equations somehow solved in a small finite set, it's very hard to predict.
That's
very hard to predict. Yeah.
Their proof is actually quite interesting. It involves maps of the complex plane which preserves all rational points. And it's a heavy-duty theorem of algebraic automorphisms. And Anderson actually is a mathematician. Both are called Greg for some reason, but one of Greg Moore also probably knows this stuff. Anyway, let's not go into it. We'll just assume it for this talk. And also, in 4D, if you work in field theory on flat space-time, flat non-compact space-time, then supersymmetric theories or theories with fermions, you don't really need to say that there's any new structure in them. But in you have to say that you're allowing half-integer spin, which is double-valued representations. I guess that's the same thing here, except that here, so actually it's the same thing. So here, if we say the theory is bosonic, that means that none of these chiral generators in particular has half-integer spin. And that being so, the descendants are always integrally spaced in level above the primaries. If you do have fermionic generators, then they can be half-integrally spaced, and you can also have complications like GSO projections or whatever. So I'll restrict to bosonic, though there are results in the same lines as what I'm doing, quite recent in the fermionic case, and I might mention some. Okay. Now, what do we know about classification to date? All unitary rational CFT with 0 less than C less than 1 are classified by BPZ. And for there are certain C values between 0 and 1 for which there exists one or more theories. There are also many C values for which there doesn't exist anything. But we know the answer in every case. Now at C equals 1, which is a famous barrier, all unitary rational CFT with C equals 1 are conjecturally classified by these authors into an ADE series. And so there are infinitely many, all at the same central charge. I believe I thought it was a theorem. People tell me it's still in principle not excluded, that there could be something else other than what these authors wrote down. Okay, now there's no rational value of C greater than 1 for which all unitary rational CFTs are known, none at all. So you can see that the problem, despite 40 years of work, needs to be specified more carefully before we can get any answers. Can I do something about this AC? I'm freezing over here. But from which, since I'm in ICTS, let me say I morally disapprove of using AC in Bangalore. You should just ban it, and that's the end of the discussion.
Diametrical opposite.
What?
You have to make sure student is the diametrical opposite.
Oh, he wants it freezing?
He wants it.
Okay, please put that on full. I have no problem. Since we are among friends, let me tell you that the use of air conditioners, non-commercial use of air conditioners is banned in many Swiss cities. Of course, Switzerland has different climate. No, not anymore.
Okay.
Geneva is hotter than here today. Yeah. Okay. So one thing to note is that by tensoring different CFTs, we can increase the C, because every time we tensor two of them, C is just the sum of their C's.
Sorry, I'm going to ask you this.
Yeah, please.
If for rational C larger than 1, are there any unitary RCFTs now?
Plenty. Millions.
Sorry,
I'll discuss. No, I will give you in a few minutes. Okay. Well, first of all, just to give you an example, all the Krishnik-Zamolodge, all the Wessel-Minowittian theories are examples. Yeah.
Oh, because you're saying under the I see.
Yeah, always the same story.
I see. So
Yeah.
So it doesn't have to have finite number of primaries, just have finite number of primaries under the time.
That's what we mean by primaries in RC. Yeah. Okay. However, one thing to note is because C equals 1 already has infinitely many theories. So if I know that there is one RCFT at C equals C0, then if I add any integer to C0, I can simply tensor with lots of C equals 1 theories, and I can get infinitely many. So we don't expect finitely many without any further specification. We have no right to expect finitely many RCFTs, even under the general definition for C greater than 1. Although it's possible that there are, but I'm saying that if once you found a C value that's allowed, then you know that all C plus n's necessarily have infinitely many theories. Okay. Now things get
considered to RCFTs to be.
Sorry?
What is the condition that determines the RCFT?
Oh, just that they have the same the same C, the same set of the operators match 1 to 1, the correlation functions and partition function are the same. Now for practical application of this, it would be enough to match the partition function and the 4-point functions of primaries, I believe. Right?
3-point function.
3-point function even should be enough.
3-point function and the always
Right. 3-point function. But 3-point function, yeah.
We need estimations.
No, I think we don't have genus. 3-point function of the scale.
No, but
build the whole higher genus
by gluing.
By gluing.
So you need 3-point functions here and also a 1-point function on the core.
Yeah, one point on the torus. Of which
1-point function on the torus you don't need, because you can start with the 3-point function and then
Yeah.
I think that the statement is that if you want to see a given set of data, 3 points, given set of 3-point functions on torus, whether it's a consistent CFT, to need the modular invariance of the 1-point function of the torus and crossing symmetry of the
4-point. Thank you. That's correct. Good. Okay. Now things get better if we specify the rank of the CFT, which is the number of primaries. And then we have a theory which actually came out of this Anderson-Moore work, followed by Moore and Seiberg's work of the same year, which is the mathematical theory of modular tensor categories, which for physicists is just the same as the classification of topological field theories in 3 dimensions, Simons type field theories. In this theory, we are given some allowed values. So when we classify these, which mathematicians have been heavily working on, then we know allowed values of C and H up to in some integers, as well as some modular transformation matrices. And between that, we have all what you call the data of the MTC. And now we can try to classify the rational CFTs of that given rank and each MTC one by one. I won't be going into that here because I'm actually not going to talk about actual classification of CFT in this talk. This is more in the direction of motivation. But in a previous talk here, for example, I have talked about that in some detail. So it's not strictly relevant now. Okay. Now, nevertheless, just to complete this part of the discussion, if we do want to classify, if we want to pose the problem as classify all rational CFTs by picking a rank and an MTC, it's surprising how little, or just picking a rank, it's not very much has been done. For example, we don't know, for example, all rank 1 rational CFTs. And for rank 1, the MTC is trivial. We don't know all rank 2, or actually for any rank. So maybe that statement was not precise. Yeah.
Please explain what MTC.
Modular tensor category is the topological data associated to a CFT, such that typically there'll be more than one CFT for a given MTC, but the data, these basic data match. Namely, if a CFT has some C and HI, then the associated MTC will have the same C and HI, but C is defined mod 8 and HI are defined mod integers. And if the CFT has an S and T matrix for its characters, then the MTC has the same S and T matrix. So MTC extracts out the fusion, braiding, and modular properties of CFTs. But MTCs can be classified just by the abstract equations satisfied by fusion and braiding. It's a long story, and let me not get into it because I'm not going to use any. You should just think of it as some topological classification such that the actual CFT is many to one map onto its topological version. Topological version subtracts a lot of data. Okay. So now a new parameter can be brought in, which is range of central charge. So we agree that C has to be greater than 1, but what should it be bounded? Supposing we say what are all CFTs of central charge between 1 and 2 of a given rank? That's a well-defined question and has a sensible answer. And we actually are quite close to knowing the answer. So Shelikins made the first highly non-trivial classification. He completed the classification of all rank 1 CFTs, which are called meromorphic CFTs, for C less than 32. So in this case, it's known that C can be only 8, 16, or 24. Actually, it has to be a multiple of 8. So if we are less than 32, then 8, 16, and 24 are the only possibilities. And we already knew that at central charge 8, there's a unique rank 1 CFT called the E8 level 1 CFT. And at central charge 16, there's E8 cross E8 and spin 32 over Z2. These two groups are famous because the existence of a rank 1 CFT at central charge 16 is the basis of the invention of the heterotic string. Because in the heterotic string, you're matching left movers and right movers in different numbers of dimensions. The mismatch of dimensions is 16 because one side is 26, one side is 10. That 16-dimensional set of left movers, which have no partners on the right moving side, are going to give you an inconsistent combination unless the left movers alone are modular invariant. And the only case when CFT's left moving sector alone is modular invariant is when it's rank 1, because then you don't have to combine it with right movers to get modular. Anyway, again, just to tell you, just to motivate you a bit, but this is a masterful work of Shelikins where he classified 71 theories at, sorry, my answer is technically wrong. There is one at 8, one at 2 at 16, and then 71 at c equals 24. The amazing thing about this work,
products.
it includes products. It includes the products. E8 cubed is one of them. E8 times SO spin 32 over Z2 is another one like that. There are a small number of such products. Most of them are irreducible. This sparked off not in the 90s, but in the 2000s onwards, several, maybe more than a dozen mathematics papers by very, very good people trying to prove his result rigorously. They succeeded. They found other proofs. It has gone into the whole theory of vertex operator algebras, which is a very beautiful field in mathematics. And it still remains a very live field there. It's completely dead field in physics because no one is interested in broadly in these problems. And except for the application to heterotic string, I think it's considered largely forgotten. But it's very significant because in the way I phrase the problem, you can see that this is the answer to that problem at rank 1. Classify all rational CFTs with a given rank and some range of central charge. And just to tell you how hard it is, at c equals 32, we already know more than 1 billion theories. So, and they're not, all are not classified, but they're at least 1 billion. There's a mathematical lower bound on the number, as well as a very large number of examples are known. So it's a huge and very intractable problem. Okay, now the next step was actually taken just 3 years ago by myself with Brandon Rayhorn, who was then a PhD student at Stanford. And we classified all rank 2 CFTs for central charge less than 25. And that's a story I've actually spoken about it here before. I won't be touching on it today, but we found 123 theories. And then in an extension of that work to rank 3 and 4, Brandon on his own found another 600 in this with central charge in this range for rank 3 and in that range for rank 4. And that's pretty much the end of it. So you can see that there's been only sporadic interest and there are only sporadic results. Higher than rank 4 for various reasons becomes difficult. Higher than central charge around 25 becomes difficult. There's also a parallel result for fermionic CFT, which was done by 3 independent groups. These are mathematicians. This is Brandon, who appeared here, and this is Tachikawa and friends. So that result also exists. Okay, good. Now I'll come to the main point of this talk. So supposing we can't really classify things easily beyond what is already done, then it's useful to consider constraints on the possible existence of theories. So the idea is to use symmetries and other properties of CFT to find candidate CFTs such that at least we know for sure that any true CFTs must be a subset of those. We also know, as it turns out, that this set of candidate CFTs is way too large. We can also prove that many of them cannot be CFTs, but inside them will lie the CFTs. So that's a worthy enterprise, and it's basically the conformal bootstrap program. So we just use basic symmetries and properties that follow from conformal invariance and constrain the possible outputs we can get. And one such important symmetry or property is called modular invariance of the partition function. And that's the basis of the program that I'll be talking about here. And it was actually initiated in 1988 by Ashok and Samir Mathur and myself. And we made some progress there, which actually went into the papers I've told you about on the previous page. But I'll now try to generalize those ideas in some different direction that we did not anticipate in 1988. Although in principle, we could have actually. If we had really kept working on this, we might have found whatever I'll be describing now in 1988. It was a hidden fact about the system we were studying, which we actually didn't recognize. Yeah, so I'll come to that. Good. Are there any questions up to now? Okay, so the partition function of a rational CFT is a bilinear combination of characters. And the way to think of that is chi of Q is the sum over only holomorphic descendants of a primary, of the ith primary. And although only L0 appears here, the trace is actually taken over descendants under the full chiral algebra. Okay, you could also dress this up with more things like J0, W0. But doing so would require you to know what chiral algebra you have. And one of the key points of this program is that we want to be agnostic about what chiral algebra we have. We just don't assume anything beyond Virasoro, and we let it come out of the conformal bootstrap. Okay, so those are chi's. They are holomorphic, but there are many of them, one for each primary. And then in a bilinear way, we combine them with anti-holomorphic characters and with some matrix that multiplies it. And then the matrix has to be chosen such that Z is consistent. And the consistency of Z is that it should be modular invariant, which I'll come to on the next page. Okay. Now, these characters, we'll be analyzing their properties soon. They're holomorphic for, Q is e to the 2 pi I tau. Tau is the modular parameter of the torus, which I think we are all familiar with. And characters are holomorphic as long as tau is anywhere in the interior. But if tau goes to I infinity, which is the degeneration limit of the torus, there they are typically singular. And that actually comes from this q to the minus c by 24 factor, though some of these also could be negative, but certainly this term is negative. I probably wrote some, this is correct. This is correct. Yeah, so even this can be negative. I mean, what am I trying to say? Minus c by 24 definitely makes the identity character have this singularity at infinity, and then depending, unless C is negative, but here I'm only going to restrict to unitary CFTs where C better be positive. And then L0, it could have a few positive eigenvalues, but they may not be. There may be many terms in this sum which will be have negative powers. But in any case, these powers are fractional. So even if they are positive, you would still say that it's singular when you go to I infinity. Tau going to I infinity is the same as Q going to 0. So fractional power of Q near Q equals 0 is like a branch cut, or like a singularity. Yeah.
Yeah, so this is like the trace over, like Virasoro module built over the I.
No, the full chiral algebra module. So
You have this J minus 1.
whatever we have, we don't know it. We just assume there is something. Whatever it is goes into the trace.
But then by agnostic, you mean you are not considering the sort of that Z e to the 2 pi I mu, something like that. You're just
because good question. So by agnostic, I'm saying that these are general properties for all CFT. But one CFT might have a Kac-Moody algebra and one might not have a Kac-Moody algebra. Okay. In the one which has, I can put a J0 up here and Z to the J0, some fugacity. And depending on the rank of that algebra, I can put many fugacities.
Yeah.
But then in the other theory, which doesn't have that algebra, I can't put any fugacities.
Right.
So then I don't have a general definition of character that spans all theories. So this is the most general you can get if you know nothing more. And since this is a bootstrap approach, you're not allowed to know anything more. Everything more has to come up.
Something that's confusing me here, which is that where is the constraint that this has to be a rational CFT?
No, there isn't one. So this is a bootstrap which gives you the space of candidate CFTs, not actual CFTs.
The sum is fine.
Huh? Yeah. Rational is is the fact that the sum is finite. And that, okay, we are going to be looking, so we'll see that when we solve the bootstrap, we will see that the C's and H's will, so we are going to solve a bootstrap which is going to give us a finite number of primaries. That makes it rational. So Moore-Anderson theorem guarantees us that C and H will be rational, and that's also what we find. So in a way, we confirm that theorem.
I see. But what was worrying me was, since you didn't put any conditions on the trace, I could have just taken any modular invariant CFT, just call that chi1 or chi0, and I could have taken the.
No, it has to be holomorphic. That's a very strong constraint. You can't get holomorphic CFTs easily. In fact, a holomorphic CFT is the most rational of all because it has to be holomorphic. All its states must be descendants of the identity. And that means there must be a very large chiral algebra and no primaries except the identity.
In that sense, it's not holomorphic CFT, but character is holomorphic. Because you're only using descendants by the chiral algebra.
Yeah, exactly. The character is
Z is not holomorphic, but I.
This Z or for a rank, you mean for the rank 1 case or in general? No, in general, of course, Z is not holomorphic. Z is because it's a bilinear of holomorphic and anti-holomorphic parts. But if I just want to make something have one character by hand, it's very strongly constrained because that character has to transform under modular transformations only by a phase, and it's guaranteed to be a rational state. Okay. So here's the modular invariance statement that if I take tau and transform it this way, and then the transformed Q, so if gamma is this matrix in SL2Z, the transformed Q is that, which is a very complicated function of the original Q, but Z of the transformed Q and Q bar should be equal to Z of original Q and Q bar. This is the statement that the theory is well defined on the torus in the path integral sense, because the torus actually doesn't know the difference between tau and this transformed version of tau, because it's a diffeomorphism of the torus. So this is a constraint which comes from equivalence of operator and path integral quantization, essentially. And now we are going to see what we can deduce from the constraint. Now, this is a constraint on this bilinear combination, which is written here, this one here. What does that constraint tell us about chi's? So the answer is that chi's must, under Q going to Q gamma, they must transform into a linear combination of themselves. So think of the chi's as a vector whose index labels the primary fields. So 0, 1, this I 0, 1, 2, 3 goes over the different primary fields of the theory. Then they can all go into each other, preserving the bilinear form on the previous page, this one. As long as this bilinear form is preserved, Z will be modular invariant. And so the statement is that the characters must be vector valued modular functions, which means thinking of them as a vector, they're not modular invariant, but they are invariant up to a rotation of the basis. So the set of chi's is the same linear span as the set of chi's before the modular transformation. And for this to make Z invariant, that matrix Mij which appeared in Z has to be preserved by rho dagger. That again you can see from this equation, because rho and rho dagger acting on the two sides of M, if they give back M, then this is invariant. And in fact, in the simple examples I'll discuss today, M is always identity, so rho is just a unitary matrix. So rho is what we call the modular representation. As we know, in SL2Z, it's enough to understand the T matrix and the S matrix, then rho is just some product of them. So we never need to know more than just the T and S matrix as it acts on the space of characters. Okay. Now let's expand out the formula for the character. I wrote it earlier as a trace, but now suppose I evaluated that trace, I would get some number. So it would start with Q to some leading exponent alpha, which is actually, we know, is minus C by 24 plus H. And then all the powers of this are integral powers of Q. That's just the statement that I'm summing over descendants. And then these A's which multiply the powers of Q, they must be positive integers, which tell me the number of descendants at that level. So AI2 is the number of second level descendants over the ith primary, like that. And it will be a complicated number in general because those descendants could be due to some unknown chiral algebra, and then some of them might be null vectors and they'll disappear from the spectrum. So in general, we don't know the answer. Okay, now I've introduced a new integer p, which is probably not a very wise choice. That's the total number of characters. I'll make a little comment soon that characters and primaries are not exactly in one-to-one correspondence. It's a slightly annoying subtlety, but we'll just let me get over with it right now. So the point is that in systems with certain symmetries like complex conjugation, the character of a field of a primary and of the complex conjugate primary is the same. So for example, in an SUN theory, the n representation and the n bar representation have exactly the same group theory. If you keep tensoring them with adjoints and other things, you just get the isomorphic answers. So the n and n bar, though they are distinct primary fields of SUN, they have the same character. And so we risk overcounting characters if we have one for each primary. So actually we should have one for each. So we should have a label I that only runs over the number of independent characters. So the procedure I'll describe doesn't work well if I double count characters.
In your display, you never said that the characters were distinct.
I didn't, and in fact, you can write it with distinct characters. It's only for what I'm going to do below that I'll show you why in a minute. That the distinctness of characters will become essential. It will turn out that they solve a certain differential equation, and coincident solutions in a differential equation is very bad. So you want them to be linearly independent, and that fails when this happens. So we should restrict to independent primaries, independent characters.
But then the modular transformation, does it happen in the...
Good. So the modular transformation happens both in the full space and the restricted space, but the properties we require of the modular transformation, such as that the S matrix is unitary and so on, must happen in the full space. In the restricted space, there's still an S matrix. It won't be unitary, but it will still have other properties like squaring to the complex conjugation, and some basic properties will still hold.
And if the S dagger MS will still be yeah.
That is still M. Yes, S dagger MS will still be true, but
no, even P1, right? Once you write
But there is a different M.
different
M. Yeah.
Take the original M and collapse.
Yeah. In fact, a trivial example is imagine M is diagonal 1, 1. There are two characters, independent characters. But let's say there are three primaries. So, sorry, take that back. Supposing there are three primaries and M is 1, 1, 1. Now I collapse two of them because they have the same character, then M is diagonal 2, 1. So it's not 1, 1 anymore. So it changes the constraint on S. So S won't be unitary. It has to preserve this matrix 2, 1. So it's different, but you can, I mean, from the bigger to the smaller is an easy passage. From smaller to bigger is something we worked out in 1989 in very great detail in examples, but I don't think there's any general theory of that yet. Yeah, okay. So these, as I said, must be positive integers. Remember, I'm doing something like a bootstrap, so I don't know what theory I'm working with. I'm only giving general properties. And I will claim that when something satisfies all my general properties, then I have some candidate for the candidate to be CFT, and bootstrap only generally returns candidates or space of allowed solutions. Inside that space, it doesn't guarantee you that every point is an allowed solution. So we are working towards that. Okay, so therefore we define admissible characters as those which are vector valued in the sense I mentioned earlier, but for which all these A's are integer. Now, one problem is, of course, nothing stops me scaling the whole thing by an overall multiplication. So the question of them being integer might be ill-defined. But there's one constraint which says that when I is 0, then is the identity character. And the identity field is unique. That's an axiom of QFT. Therefore, in the identity character, the first term has to be 1. So this number has to be 1 when I is 0. Okay. When I is not 0, it can be any integer, since we don't know the theory. So then the statement is that for some choice of integer, the remaining coefficients will be integer. And I'll show you very clear examples where you'll see why why this is a meaningful.
You said that the characters are unique.
Yeah.
You want the first term of every series to be 1?
No, because so different i's run over different primaries, yes. Right? Now, supposing my primary is, again, to bring back that example, is in the n of SUN, then the number of ground states in that module is n, not 1. So there's primaries have degeneracy, ground state degeneracy. The degeneracy is the number of the primary itself. Now, of course, you could, the point is that since we are working with the full chiral algebra, it groups, you would think that the n of SUN are n different primaries from Virasoro point of view, but the current acts on them in a certain way, treating them as a collection. So it's more natural to keep them together. Yeah, so this is the full set of bootstrap requirements, that the characters be admissible with these criteria and that they transform as vectors under the modular. These are the bootstrap requirements. Okay. Now I'll talk about this old method which we developed to, in principle, construct all admissible vector valued modular forms using a class of differential equations called modular linear differential equations. And they're classified by two things. One is this order R, which is the order of the equation, namely the highest derivative in the equation. And suggestively, R stands for rank, but now I mean the reduced rank. So the rank is the number of, assumed to be the number of independent characters. Okay. Again, since we don't know the solution, we are fixing the rank and then the characters will pop out. Okay. But there's one more integer which it turns out is essential in this classification, and that's called the Wronskian index L. It's a positive 0 or positive integer. And I'll explain on the next 2 slides what it is. But importantly, we neither assume what is the chiral algebra, nor we assume the value of central charge. These are not assumed, these are outputs of the thing. We also don't assume what is the modular representation. So S and T have to come out from this procedure. So it's a lot we are asking from a procedure giving it only very, very basic minimal data. Okay. Now for the rest of the talk, I'm going to be in rank 2 because that's what I want to report in any case. If people are interested later, I can tell you what little is known for higher ranks. Something is known, fair amount is known for ranks 3, 4, and 5. And after that, essentially not much. Okay. Okay. That also mirrors what is known in modular tensor categories. They are completely classified up to rank 4 only as of now. Okay. So here's the approach. So the idea is, let's imagine that chi is a holomorphic function. I've called it a function of tau, but same thing as a function of q. But I'm treating tau as the variable because this is a differential equation that I'll write for tau. So it's a differential equation on tau space, which is moduli space. And the idea is, supposing I have such an equation, first just think mathematically, this is an abstract equation. What it does is, there's a differential operator d by d tau, which is this, but it's corrected by something which behaves very much like an affine connection in relativity, such that if chi is modular, then d tau on chi is again modular, and I can act with d tau as often as I like. I have to keep increasing k because it's the weight of whatever it's acting on. It's similar to how in relativity we keep changing our covariant derivative if it acts on higher and higher rank tensors, because there are more and more terms when it acts on a higher rank tensor. So I use that derivative and I assume a second order differential equation. So the most general one is with d tau squared, d tau, and 1. And in this case and this case, I give it coefficients, which I call phi 2 and phi 4. At the moment, I treat them as arbitrary functions of tau.
Sorry, I can understand.
Yeah.
You're saying this based on the earlier paper, but could you give some intuition for why it has to be that the modular constraint gives rise to this kind of difficulty?
Yeah, no, it's coming. It's coming. Right now, as I said, I'm just asking you to understand what the equation is. And in next two slides, we'll see why we want to use this to solve our bootstrap problem. So this is an equation. But the nice thing about this equation is that I can make the whole equation modular invariant under SL2Z, which means if I perform an SL2Z transformation on tau, then this being 0 maps to the same thing being 0. Okay. To do that, I have to make sure that phi 2 and phi 4 are themselves holomorphic modular forms. If I manage to make them modular forms where phi 4 has weight 4 under SL2Z, phi 2 has weight 2, and d tau by itself is known to have weight 2. That is, when it acts on anything, it increases its weight by 2. That's the analog of a statement in GR that if covariant derivative d mu acts on a tensor, it gives you a tensor of 1 higher rank. D mu on, let's say, V nu gives me a second rank tensor from a first rank. So this increases the modular weight, which actually I didn't define, but you can sort of imagine that modular forms have some weight under SL2Z, then d augments by 2. So d squared augments by 4, d augments by 2, but then phi 2 also has weight 2, so the total weight is 4. Phi 4 has weight 4, so all these terms have weight 4. That being so, under modular transformations, the whole equation will get a net weight 4 factor outside, but it's a homogeneous linear differential equation, so that factor is non-zero, so the equation remains invariant. That's the idea of a modular invariant differential equation. Okay, the most general linear second order modular differential equation looks like this. Now, why do I want to use it? How do I want to use it? Well, first thing to note is that if I know these functions phi 2 and phi 4, then this equation has 2 unique solutions and then all linear combinations. That's just theory of Fuchsian linear differential equations. So it's pretty easy to solve, at least recursively in powers of q if I know phi 2 and phi 4. Okay. The interesting thing is If I solve it, I'll get two independent solutions, which I can label chi0 and chi1. And it's guaranteed that if this equation is modular invariant, then those two solutions must transform as a vector-valued modular form. So this equation is a proxy for discovering vector-valued modular functions. And it works both ways. If you have a vector-valued modular function, then such an equation must be true, and they must be the two linearly independent solutions of such an equation. And if such an equation holds, then its two linearly independent solutions are vector-valued modular functions. Moreover, the solutions will, of course, it's a linear space. There are two solutions, so any linear combination is also a solution. But there's a unique basis in which each solution has a distinguished power of Q as the leading power. And so therefore, we actually get a unique pair of solutions. Okay, so this is the idea. But the problem is that for a generic equation, the solution may not be admissible. In fact, we'll see that for a generic equation, the solution is not admissible. Okay, but you might be able to specially choose these functions phi2, phi4 to ensure that the solution is admissible. Now, so I'll come to how we choose those functions. So we've seen that every modular differential equation gives a pair of a vector of modular forms. Now I'll show you that every pair of vector-valued modular forms arises from such a modular differential equation, and it will give us some insight into what these phi2 and phi4 mean in terms of these vectors. So supposing I'm given one vector-valued modular function, chi0 and chi1. You see, this discussion is very simple in rank 2, though you can easily generalize it to rank n. Supposing I'm just given two such functions, and I'm told that under SL2Z, they transform into each other by a modular representation. Now, supposing chi is an arbitrary linear combination of these, then it's obvious that this determinant must vanish because the last column is a linear combination of the first two columns. Now I expand this determinant by the last column, and I get this equation where some determinant involving the known quantities, remember I'm given chi0 and chi1, appears in each of the terms, and the unknown quantity chi is satisfies a differential equation of the form I wrote earlier with these coefficient functions. But the form I wrote earlier didn't have any function here, so I need to divide the whole equation by this first determinant, and I get phi2 is this and phi4 is this. So what I've shown you is that if I'm given chi0 and chi1, I can recast them as the independent solutions of this differential equation with phi2 and phi4 being of this form. It's quite beautiful. And what you see here is also a very important fact. Chi0 and chi1 being characters are not supposed to have any singularities. You can actually prove that they don't have any singularities in moduli space. One way, if you're interested, one way to prove it is that actually their behavior is bounded above by the partition function, the whatever, Hardy, Ramanujam, whatever, the usual partition function, because that's the maximum, and you can raise that to some power. That's the maximum number of descendants you can have given a chiral algebra. And then, whatever the theory actually has is less states because there could be null vectors. So with that upper bound, you can show that the characters must be holomorphic, but note that phi2 and phi4 are not holomorphic because this determinant in the denominator can have zeros, perfectly allowed to have zeros. And whenever it has zeros, if the numerator doesn't also have them, then these will blow up. So there will be simple poles. That's a very important fact. It's so important that a lot of mathematicians and physicists missed it in the 1980s to a point where there's categorically wrong paper claiming that these have to be holomorphic functions. And it's published in the same month in Nuclear Physics. He has another paper solving this equation for a case where phi2 and phi4 have poles. So, even in our community, people don't read each other's papers. And yeah, so I will, so this is just to say that these functions can have poles. And now we have to say something about those poles in order to know the functions.
What you showed us, refers for any second order linear differential.
Yes.
Which is always true. If you give me two solutions, I could derive the differential.
That is true. That is why it's called the Wronskian method. This predates probably modular invariance as well. However, the new thing is that if the equation has a symmetry like SL2Z, then the solutions have the linear span of solutions has the same symmetry. And vice versa.
Phi 2 and Phi 4 will be actually invariant or over.
And Phi 2 and Phi 4 are invariant. You can actually easily show it because now if chi0, chi1 transforms as a vector, that's a linear transformation between this first column and second column, and that just gives you something outside, and the same thing comes out from the denominator. So
it's invariant.
So it's invariant. Invariant up to a weight. So what happens is because of these d's, the weight of this numerator is actually 2, and the weight of the 4, and the weight of the denominator is 2. Therefore, the weight of phi is 2. It's the d's which give the weight. In the second case, the weight is 6 because there are 3 d's in this determinant and only 1 in the denominator. So 6 minus 2 being 4, that is. So that's how you get the modular weight. So the modular is added on to a general theory of differential equation. Yeah.
One thing about the characters,
Yeah.
can they have zeros apart from the cusps?
Yeah, they can have zeros anywhere. They can not characters. Okay, characters. Yeah, it's these determinants can have zeros. We don't know what the characters are doing. Characters are unlikely to. They could, but it seems.
Easily at q equals 0 inside the fundamental.
No, that is the boundary of the fundamental. There they diverge. There they can cheerfully diverge.
Partition function has a 0 there.
Yeah, that's when q goes to 0. It can either have a 0 or it can diverge. Typically, it diverges because its partition function always starts with negative powers of q in a unitary theory.
Sorry, I meant the Hardy-Ramanujan, that.
That one, of course,
zero only at the cusp.
Yeah, what happened, Surat? You seem to be struggling with the. You want to move somewhere to a better air conditioner?
But is any running?
I'm sure one of them will. This beeped and went off.
Yeah.
Also, strangely, these mics have red lights and those mics have green lights, so I'm not sure what it means. Okay. Okay.
He's gone. Yeah.
Okay. Good. So this shows that phi 2 and phi 4 can have poles whenever this particular denominator, which is this one, the red one, has any zeros. Okay. Now, since we are doing bootstrap again, we don't know how many zeros or poles there are because we don't know these solutions. We just know that it could have. So we should parameterize that problem. And we do so by giving a name to the number of such poles in the interior, not counting the behavior at the boundary of modular space. And we just call it L by 6, where L is an integer, which is called the Wronskian index. So why do we call it L by 6? That's because this torus moduli space has these cusps. And at the cusps, you can have a fractional pole because the cusps are really orbifold points of that space. So the two, sorry for this, but
they're called elliptic points.
They're called, something, And there's also one in the middle. So there are
one at I and one at
one at I
by 3.
Yeah, one at I and one at 2 pi I by 3. I can draw that for you here. So the point here is that this point, and this point are special. This is actually the same as this point, so there's an identification that this plus this circuit brings me back here. And here there's also an identification because this line is folded. So this is a order 2 and this is an order 3 orbifold point. And the result is that you're allowed 1/3 pole at that corner and 1/2 pole in the middle. And so with the general rule, if you make a linear combination of 1/3 poles, 1/2 poles, and full poles, then it can be well parameterized by just the number L by 6, and L cannot be 1 in any case. It can be anything above 2. Or it can be 0, of course. Okay, so this is the Wronskian index. Now, so I explained the factor of 1/6. Now, Nesulich wrote a very nice paper following our work and showed that when you have 2 characters, which is the case of interest, L is even. So in general, L can be odd also. And it will play an important role in what I have to say. So L is known to be even for 2 characters. Good. Now, now let's see the use of having defined L. Given any L, there's a finite basis of functions of two modular functions, the Eisenstein series E4 and E6. These are special modular functions which transform with weight 4 and 6 under SL2Z into themselves, and they are holomorphic. And they span their polynomial ring, which means any powers of both of them, spans all modular forms of SL2Z, which is a remarkable fact. So, therefore, if I want, for example, to find a form phi4, and I know L, I follow the following algorithm. If L is 0, phi4 is holomorphic, it can only be E4 up to a number, multiplicative number. If, on the other hand, phi4 is not holomorphic, so L is non-zero, then phi4 can have some denominator. So, for example, it could be E6 upon E4 the whole squared. Then it will inherit the zeros of E4 as poles. So, like that. So, you can find suitable phi2 and phi4 as functions up to some free parameters for every L. That's the key point. So the modular differential equation ends up having finitely many parameters, and that number grows as a function of the Wronskian index L. So you can guess correctly that the problem will become harder as L goes up. But we could ask questions like, what are all the admissible characters when L and L is a small number? The purpose of today's talk, however, is to address that more difficult question. What about arbitrarily large L? But I'll build up to it slowly. Now, looking at that modular differential equation and the fact that L is the number of zeros of a certain determinant, and knowing the modular weight of things in that equation, you can, and doing the, this torus space that I drew up, this upper thing is isomorphic to a sphere. And so what you can do is just add up poles and zeros and say that it's a holomorphic function. So sum of poles and zeros is 0, counting also fractional poles. And we get this relation between the Wronskian index, the central charge, R, the order of the differential equation, Hi, the conformal dimensions of the solutions, and those are the basic data. Now, you may say, what are C and H? I don't have a CFT yet. They come from the exponents in the equation. So the equation, if you remember, the characters start with q to the alpha I. Each of those alpha i's is minus c by 24 plus hi. So I just give them the name minus c by 24 plus hi. I don't know that these are c and h of anything, but since there are some numbers, I can parameterize them this way. And then this is, if I had written it in terms of the hi minus c over, oh, that way, yeah. So actually, each of these, together, these two terms are nothing but the sum of minus 6 times c by 24 minus hi. Yeah, I could have written it in many ways, but anyway, this is the answer. And by the way, this has some interesting consequences which are not fully explored. These are rigorous statements about any rational CFT. Yeah.
It's a Riemann-Roch for torus, which is giving us.
No, it's really for the sphere. So it's even not even really Riemann-Roch. It's just for the sphere.
Riemann-Roch on the moduli space.
On the moduli space, which the moduli space of the torus is a sphere. So that's that's
after those one.
Yeah. So it's a sphere with some points on it, but those points you can simply allow fractional poles. In fact, even at infinity, we are allowing fractional poles. That's why C and H can be fractional. So even though they are appearing in a sum, which I'm calling poles minus zeros, they are fractions. That's all allowed.
And by that finite number of parameters, you're saying that because but for
that I haven't come to finitely many parameters. I will show you in a minute. Okay. I just made a general statement that since there's a finite basis of functions of these things, and that basis is fixed by L. Okay. So the functions are determined and the parameters therefore can only be what multiplies them, and I'll show it to you concretely.
It's Riemann-Hurwitz.
Riemann-Hurwitz? No, I think this is variously called Riemann-Roch or Valence formula, or also one more name which I've forgotten. No, this is not Riemann. This is not that fancy. It's actually literally the statement that on a sphere, if you have a meromorphic function, the sum of its algebraic sum of its poles and zeros, that is poles minus zeros, must vanish, or must be equal to 2, whatever it is. 2.
On a plane, it varies, depending.
On a
On a theory it will vanish, probably on a plane, you may have some factors of yours.
Yeah, something like that. Okay, so one consequence is, supposing we have fixed rank R, that is fixed number of primary fields, then the only way L can be large, if L is large, then C must be large. So when C is small, you can't get large L solutions. Similarly, supposing we fix C, then L can only be large if the rank is large. That's the only thing that can make the right side large. I'm always assuming C is positive here and H's are also positive. Okay. So these are just interesting facts. It's interesting that this has not gone into much discussion of CFT in the 80s, even though this is a known result. In fact, the yellow book only mentions that this quantity on the right side is known to be greater than or equal to 0 in any rational CFT. Doesn't give it a name and doesn't talk about its significance.
What is it? How do they derive it?
I don't think they derive it. It's an exercise, but
Just an observation.
but I suppose you can just derive it from the set of the way it's just the sum of exponents. The only non-trivial term here is the last one, and this is the weight of that Wronskian determinant. Sorry, this is also this is correct. It is r minus 1 over 2. The weight of that determinant is because it is r minus 1. This comes from that. Okay. So now a little digression. Oh God, it's already 4:30. I promised Ashok I'll finish by 5. Because he has to leave at 5. But 5 is a good time to end.
This thing is recorded, right?
Yeah. Okay. It's not going very fast, I must say. Anyway, this is a quick digression then. You can calculate, since this Wronskian index is a nice thought, which was not, studied in the 80s. You can ask, we know so many rational CFTs, what is their Wronskian index? Turns out all C less than 1 minimal models have L equals 0. All SU2 level K Wessumino-Witten models have L equals 0. All A, B, and D Wessumino-Witten models at level 1 have L equals 0. This we all calculated in 89. These authors more recently extended our calculation and showed that also in all these cases, the Wronskian index is 0. But that also tells us that in any other case, which leaves plenty, for example, all A, B, C, D at levels greater than 1, the Wronskian index is greater than 0. So we don't know what it means. Okay, we have rank 1 CFTs of central charge A10, the ones classified by Shelikins. In their case, it's very simple. If the central charge is A10, the Wronskian index is 2n. You can get it from the formula I wrote by specializing to rank 1, because then the rank term drops out and the H term drops out.
So why should this be?
No, maybe it doesn't. I agree. Nobody has found that it means anything. What is the pattern? We don't know. Does the Wronskian index have a physical meaning? We don't know. But it's also true that the models that most people appeal to when they discuss rational CFT for any reason whatsoever are either C less than 1 minimal models or SU2 at level K. And therefore, most people have never come face to face with a L not equal to 0 CFT. In fact, until 2018, when I started working with Ramesh, it wasn't known that there are any rational CFTs with L greater than 0. I'll try to convince you that there's an abundant infinity of them.
So I'm confused. The SUN at level K, people do often study.
Not really. Concretely, who studies K greater than 1?
Okay, but let's say you just wanted to compute this value of L.
Yeah.
Then that is a question of computing
the C's and H's. You don't need the characters, you just need the formula for C's and H's. Knizhnik-Zamolodchikov.
Oh. And one would just get L.
You just get L from it. Okay, coming back. So now, so the simplest thing to do is take it to be 0 and ask what you can do in that case. And that's what we did in our first paper on this problem. Now, when it's 0, it's known that there's no holomorphic modular form of weight 2. So phi 2 is not there in the equation. And the only one of weight 4 is E4. So there could be a number in front. And therefore, the equation I wrote earlier collapses to the much simpler equation, d tau squared plus mu E4 on chi is 0, where E4 is a known function of tau. So that's an equation. So it's worth studying because its solution necessarily should include the characters of all L equals 0 rank to CFTs. And the solution is completely determined by one parameter. So a lot of simplification from what the equation could have been due to modular invariance, and then the choice L equals 0. Okay. Now you insert this solution and you parameterize the leading exponents in this way. And as I said, it's just notation, but if these are CFTs, the characters, then of course that C and H will have the usual meaning. And in lowest order, we find that mu is just the parameter of the equation is just this. We still don't know C. Once we go to higher orders, we simply have to do that. We simply scan over values of mu, real values, and we try to see that every successive coefficient in the solution is a positive integer to get admissibility. And I'll show you how the miracle works. Supposing we inserted C equals 14 by 5 into our equation. That determines mu, as I just told you. This is the solution we get order by order. And you can do this to any order you like. And notice that the first one is completely integral all the way. You can calculate as high as you like, and it's integral. The second one, not so much. There's a 34 by 7 here. Everything else is integral. Only that term has a denominator. But if I normalize this by 7, so I start with 7, then it turns out everything is integral. Okay. And once I do that, it turns out that this can be identified with the Vesuvino-Witten theory of G2 at level 1. G2 has dimension 14. This is the number of descendants of the identity under the 14 currents of G2. That's that 14. And G2 fundamental has dimension 7. That's the leading term when you correctly normalize it. So you see that group theory comes out of this modular bootstrap. Yeah.
Chi-0 transform into Chi1 under some modular.
Yeah, it does.
If you normalize it by 7, it won't.
Then it will. Now it won't.
Before you normalize
because these are two solutions of the linear differential equation. So there's nothing to tell me how I should normalize them. So I don't know how they transform till I normalize them the right way.
They are always transform into each other, right? The linear combination will change. You get
the linear combination will change, and the S matrix won't satisfy the S dagger S condition.
Correct, but you're not allowed to choose the normalization.
Yeah. No, so for every choice you'll get an S, but only one choice will have a unitary S. That turns out to be the one where you put the 7, not where you didn't put the.
Could it be that that choice was not the one that gave you integer?
Yeah, and we would be sunk. We would be sunk at that point. Exactly. So a lot of miracles happen. But then on the other hand, since we set up a bootstrap which necessarily is solved by any real CFT, if there is a CFT, it has to solve the bootstrap. So this had to happen. But from the purely modular point of view, it's a total miracle. Okay, now just to show you, if I vary this number, which I inserted into the original equation, to a neighboring number, this is the series solution. And you can see that here, there's no way that it's going to be made of integers. This one can't even be normalized. This one, however hard you normalize it by an integer, there'll always be a bigger denominator in the next order, and it's never going to become integer. So this one formally is still a vector valued modular form satisfying the modular properties, but not the admissibility. And it's very easy just by focusing on the first term, second term, third term to fix whether the thing is going to be admissible or not. And that's what we did in 1988. And this is a screenshot of the table we produced. And discounting some non-unitary cases, which I don't want to spend time on here, there are basically 7 theories from SU2 to E7, which are all admissible characters, and all are known Vesuvino-Witten models. And I'm going to focus on those 7. Okay, so that was L equals 0. Now, how do we go beyond? Well, we can write the L equals 2 equation. Turns out to have the same form, but now E6 by E4 is allowed in this. This is a phi 2. If you remember what phi 2 was, this is an allowed phi 2. The only one actually. Even the coefficient is actually fixed, so it still has only one parameter. You can again find solutions. That was done. I won't be discussing them here.
The coefficient is fixed by what?
This coefficient is actually fixed by the initial equation. So it turns out that this coefficient is L by 6. That's why it was absent in the first equation, and now it has to be 1 by 3 because L is. Yeah, it took us a while to figure this out, but it simplifies things. So that coefficient never adds a new parameter. Okay, and for L equals 4, there's a similar story, but for lack of time, I'm going to skip it. But I just want to say that L equals 0, 2, and 4 are very special because these are the cases where the MLDE has only one free parameter and the admissible solutions are easily found. And all hell breaks loose at L equals 6. And I can explain that to you in a geometrical way from that diagram, which is the following. I lost my chalk. Here. L labels the number of poles of these functions phi 2 and phi 4 in moduli space. If L is 0, there are no poles. If L is 2, it means there's one pole here. That pole counts as 1/3 of a pole, so L is 2. It can't move from there, it can't be here. If L is 3, it could be here because that's half a pole, but L equals 3 is anywhere down. I said it has to be even. If L is 4, it means there are two poles at this corner. Okay. Once L reaches 6, the pole can be here, but it can also be here, can be anywhere, because that's a full pole. L by 6 is the true number of poles. And once L crosses 6, the pole can be anywhere in this region. But then this location is a number, a complex number. Actually, it turns out that it's typically on the boundary, I think. But anyway, there's a parameter, new parameter, every time L jumps by 6. Because every time L jumps by 6, I get one pole that is free to run around in moduli space, and that's a new parameter. So this is how we see that things become more difficult at L equals 6. And not just the equation, but then the solution also ends up having free parameters. Free parameters which we
just integer expansion
and free parameter which themselves can be integers, but any integers.
But not continuous.
Not continuous. And I'll show you examples. In fact, for L equals 6n, the MLDE has precisely 2n plus 1 free parameters. And the bootstrap approach becomes very difficult. We did address it in a paper in 2023, and we found, we solved actually the L equals 6 case, but it was quite tough going, and it's not the easiest way to do things. And now I'll finally come to the topic of my talk. And this was discovered by Ramesh and myself as part of his master's thesis in 2018. And this is the method of quasi-characters, and it bypasses the need to study these more difficult MLDs. What it does is that it gives us a way to classify admissible characters for these values of L, 6n, 6n plus 2, and 6n plus 4, using only solutions to the MLDs with L equals 0, 2, and 4. Okay, so 6n comes from 0, 6n plus 2 comes from 2, 6n plus 4 comes from 4, and these I've already called the easy MLDs. Now, of course, you may say, well, it seemed like we had only 7 solutions to the L equals 0 MLDE. So what are these new ones? And that was the real shock. There turned out to be infinitely many solutions we missed, but we didn't miss them. They're just not admissible in a very interesting way. Okay. So once we know these, I claim that once we finish this process, then we would have completely solved the rank 2 bootstrap problem. We know the complete space of admissible vector-valued modular forms, modular details, and the rest of the talk is about those details.
So use the non-admissible ones for these easy ones to get admissible ones.
Yes, exactly. And I'll show you how that works. So the idea is that, when we were finding admissible solutions of this MMS equation, we threw away anything where one of the degeneracies was negative integer. We didn't say, oh, how nice, at least it's an integer. We said, very bad, it's negative. If it's negative, that's not an admissible solution. It can't give me a CFT. So we discarded them. Okay. But actually, the way Ramesh's thesis started, he went and dug into the math literature, and I really don't know how. I think you had a friend in the math department who you were talking with or something. I know I didn't start this problem, you did. It's entirely your fault. So yeah, so there are these interesting papers by Kaneko and Zagier in 1998, and then these follow-ups by these other authors, all mathematicians. By the way, a few years ago, I met Zagier, who claimed that in 1998 he invented MLDEs. So our work was from 88, so we had a little bit of clash there, but I think he was very gracious about it, and now at least he knows about our work, which predated actually his. It's the same. His Kaneko-Zagier equation is our equation, but modified by multiplying the solutions by some function. So it looks a little different, and it's applied for a different problem totally. So these quasi-characters are non-admissible solutions of the existing equations, the simple ones, but they are fairly admissible in that they still have integral coefficients. All coefficients are integral with some normalization, but they are not always positive. That's a real miracle because, all integral is only guaranteed if you have a CFT. Otherwise, it's not guaranteed. It's just a miracle. And here we don't have a CFT and the miracle is still happening. And it's a big puzzle why that happens.
How many solutions were there? How many such solutions?
So there's one infinite family for every one theory that we found. And I'll show it to you. I'll show it to you in a minute. And our key result is once you know these quasi-characters, these non-admissible solutions, you can take linear combinations of them and you'll generate all admissible characters with L greater than or equal to 6.
They can't have rational equal.
You could have, because the normalizations of these quasi-characters are as ambiguous as the ones I showed you already. And this time we don't have even that the identity has to be normalized to 1 because it's not a theory. So there's some normalization. The one in which the S matrix is unitary is the natural normalization. And it may be that both the characters start with some integral starting point. So that is an issue.
Is there some meaning of the negative integers?
Yeah, so not by itself that we know of. And the rest of the talk is entirely about those negative integers. So I'll come to it. So the only problem, so there are two problems. One is to classify quasi-characters, which we completely did actually in 2019. And the second is to study which linear combinations give admissible characters. And I'll show you in examples how it works. So here are the families. Just as there were 7 solutions to the MMS equation with central charge these numbers, now I have quasi-characters whenever that central charge is translated by a multiple of 24, exactly 24. So 24m plus j, where m is any positive or negative integer. It can be negative because I'm not looking for these quasi-characters to be a unitary CFT. They are a building block. Just keep thinking of them as building blocks, which are mathematically very miraculous. The reason I ruled out 0 is that for 0, m equals 0, they are characters and they are CFTs, and that discussion is over. So the new ones are the m not equal to 0 ones.
And these are the only ones?
These are the only ones, yes. And again, with MTC theory, you can verify that these can be the only, these are the only possible. Now, importantly,
and this includes the 140 there no CFT, the E7.5.
It does actually, but I'm not discussing it because those are non-unitary in any case. So I'm not discussing them in this.
The originals.
Yeah.
Here,
yeah, the quasi-characters exist even for that series, and they were also in our paper. I've removed them from the recent paper because we wanted to discuss admissible characters made from it. And for that, we wanted to keep non-unitary theories out of the story. Okay. Importantly, when I translate a central charge by 24 times an integer, the modular representation doesn't change. This is just a fact of rational CFT. And it's for T matrices, it's a trivial fact because C, you get only Q to the minus C by 24. If C shifts by 24, you get an integer power of Q. So the T matrix obviously doesn't change. Turns out that the S and T matrices are the same for every one of these infinite families. So that's the real beauty of quasi-characters. Now, I told you already that once I know C, the parameter in the equation is fixed to be minus C, C plus 4. So the equation is determined just by deciding to choose this. And once the equation is determined, the solution can be got by doing the Frobenius recursive method. And again, we get series expansions. And let's look at, so these are families, one for each j in this set. So we label the whole family by the CFT which arises when m is 0. So for j equals 1, we had the A1 CFT. So the whole family is called A1 family, like that. A1, A2, G2, D4, F4, E6, E7. They're labeled by Lie algebras, though the quasi-characters have no connection to those Lie algebras. Let's look at this case. So first, let me remind you, for when m was 0, we had a CFT. This is SU2 level 1, very familiar to people. This is its series expansion. And you can see that there's a 3 here, which is the dimension of SU2. And this is all positive, and it will be positive however far you go. Now let's look at m equals 1. So C is 25. Okay. In this case, you find this term is negative integer, but all other terms are positive to infinity. Just one term is negative integer. So you see, this is a miracle which, as it stands, has no explanation. It's not due to the existence of CFT that this miracle happens. And again, if I vary from 25 to some neighboring number, 26 say, I'll just not get integer expansion. But so there is a miracle. It's a special points where this happens. And this kind of miracle happens exactly at this list of values, 24m plus j, where j is exactly in that list. And we deduce this by adapting the work of Kaneko, Zagier, and other authors. But then we verified it ourselves, and it's always true. But this can't describe a CFT. Okay. And various people have suggested that maybe this is some fermionic thing, and this is some. But you know, in super traces, the degeneracies always alternate. You never have one. In fact, I asked ChatGPT whether there is any known modular form of SL2Z which has this property, some alternation till some point and then all positive, and it didn't find any, but that's no guarantee. It makes mistakes, but I've not met anyone who could show me a real modular form which had that property. So it seems to be special to VVMFs, vector valued modular forms. Okay. So let me give you another example to show you that it's more general. When m is 3, so C is 74, we get here a minus, here a minus, here a minus, exactly 3 of them. And from Q to the 6th term, it remains positive forever. And as m increases, this alternation keeps on for much longer. And there's a point where it changes. So you might have noticed the coincidence that 6 is twice of 3. In fact, whenever m is any value, then at Q to the twice that value, the alternation stops and onwards it's positive.
This is the empirical
Yes, and that's exactly why we wrote the paper which came out last week. The empirical observation is from 7 years ago, and we wrote the paper exactly to prove that. So I'm sorry I've taken this much time to get to the motivation of my talk. It's an empirical observation, and we can do it for lots of m's, but obviously there's no proof. That doesn't prove that it's true in general.
You could choose capital M equal to -1, I mean, negative stuff.
Good, thank you. So what turns out, first of all, I've only shown you the identity character. If you look at the non-identity character for positive m, it's all positive. It's only the identity character which does this. If I take m negative, the roles are flipped. The non-identity character is now alternating, and the identity character is fully positive.
It's like the non-unitary theory in which the
slightly to some extent, but not completely, because in m for negative m, a weird thing happens. This oscillation takes place in sign, but when it stabilizes, it remains minus all the way to infinity. It doesn't turn positive and remain positive all the way to infinity. It remains negative and continues being negative. So there is a peculiar flip there, which also we could explain. Now, I mean, these are all empirical facts. Okay, so let me summarize the facts. For m greater than 0, so the actual
alternating thing is needed to make sure that you get a real character after.
Well, no, if it was not there, then of course, yeah, good. The knowledge of the alternation is needed because you want to sum up these quasi-characters in a way where the minus signs get cancelled. So you need to know where they are and even how large they are. And that is why we did this last week's paper, which actually took us maybe almost a year, I must say. But and we didn't really complete the problem, but we did quite a bit. So I'll tell you about that. So for positive m, this is what you get. And you see that it goes plus ... to infinity. For negative m, this guy is good. And this one alternates till 2m minus 1 and then remains negative all the way to infinity. So question is, these are the empirical facts verified only for any m that you want to pick, but now we need to prove it. So this is the statement. And the asymptotic behavior can be summarized by saying that when m is positive, chi0 and chi1 both are asymptotically positive, but when m is negative, this is positive and that's negative. And this particular fact, this asymptotic behavior, actually Ramesh and I already explained in an appendix of our original paper. And that's because the referee asked if we could possibly try to explain it. And then we tried what the referee suggested, and it worked. So let me explain. So these are experimental facts, but we could show that we could predict that this behavior is not an experimental fact, the asymptotic behavior, that it's a general fact. And I'll show it to you. So, but before that, I need to motivate why we are studying these. I haven't told you how we get admissible characters out of them. And the basic idea is this. If I add, since all of these quasi-characters in a family have the same modular transformations, I can add them. And I'll still have the same modular transformations. So when I add them, I get a new VBMF. But miraculously, even though each term has Wronskian index 0, every time I add them, the Wronskian index jumps by 6. It's a very beautiful thing that one can show. And then we can ask the question whether this thing which has Wronskian index higher than 6 can be made admissible. And I'll show you an example which will, I think, fix the idea in your mind. So let me take two solutions, one for m equals 0, which I've shown you, and one for m equals 1, which I've also shown you. And I'll just add them, but I'll keep a number n over here, which I'll keep fixed, and it will be some arbitrary integer. And we'll try to see what it should be. When we add them, the identity character becomes this. And you see that if n is greater than or equal to 245, the non-admissibility is gone and the whole thing is admissible. So that's a kind of linear bound on n. It should be greater than that. It's quite easy, though I won't discuss it, to put an upper bound on n also, because this number is the dimension of the Kac-Moody algebra of the final theory, and that's bounded given the central charge. So actually n can't get too large.
So that's coming from some other thing.
Yeah, that's another, it's not a pure bootstrap, not mod. I agree. Now you can read off by also writing chi1. You have to write chi1 also, and the same n obviously has to appear in both for the modular property to work. And you can read off that the sum has central charge 25, but now the conformal dimension is 5/4. And with this combination, you can run the Riemann-Roch theorem in reverse, that we know C and H, ask what is L, and we find L is 6. So adding two of these guys, both of which have L equals 0, the sum has L equals 6 and is perfectly modular. And so it's not hard to guess that this, Sumati has come. I'll tell you the rest of the summary tomorrow. Okay, see you, sorry. Okay, now it actually generalizes the way I said, namely if I add n plus 1 consecutive quasi-characters, consecutive means the m values have to be consecutive.
The value of L was insensitive to the choice of n?
Yes, it's insensitive to the choice of n, because it only comes from the exponent. And the beautiful thing is that in the identity character, the leading exponent, the most negative one, is the central charge of the higher guy. While in the non-identity, the most leading gets a contribution from the lower guy. And that's why this weird thing happens. And we get this answer, 25 and 5/4. Okay. Actually, if I'm not mistaken, this one on its own has central charge 25 and H equals 9/4. And this has central charge 1 and H equals 1/4. And so the H in the end turns out to be some average of the two, but it's not a guess. You can read it off if you like. It's basically comes from the Riemann-Roch constraint. Okay, so if we add n plus 1 consecutive, we get L equals 6n. Now we also found quasi-characters with Wronskian index 2 and 4. For simplicity, I won't discuss them today. These were not discussed by Kaneko, Zagier, and other people. So this L equals 2 and 4 quasi-characters are entirely our doing. And once we found them, then you can just take their linear combination and you have got all possible admissible characters for all possible L. So it solves the bootstrap problem completely. It's less exciting than you may think because it still gives a huge space of admissible characters, and there are not so many CFTs in that space. In fact, you may question whether there are any. So at least I'll show you that there are one or two. But in fact, there are more than that. But it's not that this solution to the bootstrap is anything like a solution to the classification problem of CFT. It's way too big. But it's a solution. It does tell you that there are no CFTs outside that space. And it's quite a non-trivial space. And we were able to prove, this was with some help from Ashok. So this I presented in an ISM in Trivandrum. And Ashok asked a question, which then Ramesh and I discussed with him later. and we realized that actually this is complete, that if you ever have an admissible two-character VVMF with any L, you can prove that it's made up of quasi-characters. How you prove it is that you subtract a quasi-character from it and keep lowering its Wronskian index till you reach 0. And then that means that the original was the sum of quasi-characters. It's very pretty. Okay, good. So now let me quickly describe our attempts to prove the conjecture properties. And this is quite ugly and technical, but it's important. So I'll just run through it very fast. The solution of this differential equation is a recursion relation for the coefficient an as a sum over all the coefficients an minus I, all the lower ones. Now, this is a particularly bad form of recursion. People like recursions where an is given entirely in terms of an minus 1, which is given in terms of n minus 2. Is not like that. You need to know all at every step. It's sort of triangular in that way. It's very hard to sum up in any sensible way. And if you could, you would have solved a generic modular differential equation, which nobody thinks is possible. So we have to do something, and we are going to make some approximations. So what does this function look like? It can be extracted from Eisenstein function series E2 and E4. And these are some divisor functions which are part of the Eisenstein series. And otherwise, it depends on M, which labels the central charge, and these small numbers J, which label the family. So this is the formula for the recursion coefficients. And we want to solve this recursion approximately. Now, approximate cannot be used to determine admissibility, but luckily here, we already have integrality done for us. We don't need to prove integrality, so we can do approximations. And let's do a warm-up exercise. Let's first look at the an coefficient when n is much larger than m. This is the limit where I'm late in the series for a fixed central charge, finite central charge. Here we only want to see asymptotic behavior. And the other extreme limit is when mod m is much greater than n. That's very large central charge for fixed coefficient in the series. And here we expect to see the alternating behavior, because remember, this alternating behavior takes place until n reaches 2m. So in this limit, it's very much present. So we should see it. We should prove it for general n and m. And we use the Rademacher formula as adapted by Moore and company for vector valued modular forms. And here appears the modular S matrix. And we know the S matrix, for example, in the A1 and E7 quasi-character families, it's that. In G2 and F4, it's that. And it's also known for the other cases. And note that it has the signs plus, 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 minus. And that turns out to be exactly the reason why the coefficients for large n go like plus, 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 and minus of some exponential. And so the asymptotic behavior is indeed positive, 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 and in the last case, negative. The non-identity character of m less than 0 is asymptotically negative. So it's actually works. This is already in the appendix of my paper with Ramesh. So it confirms something for general m. So that's something nice. Okay, now the opposite limit is more interesting. Here, we assume the central charge is large, and we put that limit into the Frobenius recursion, and it simplifies to this. And now we note that at every stage of recursion, you gain a factor of m, which is large. M is c by 24 roughly, and m has been taken large. So now you can actually assume in this recursion that it's a one-step recursion. That is, an is just related to an minus 1 and n minus 2 and so on, because that will be the leading power of m. It will be the nth power. So you neglect all the other terms and you find that a0n goes like minus this number to the nth power. And now we have an illumination. If m is positive, you see that this is alternating with n. And if m is negative, then it's not. This is the identity character. So exactly what we expected. Okay. So this is very beautiful. The non-identity character similarly works out. And so for low values of n, that is the early coefficients in the series, but large C, we have confirmed the general property of quasi-characters. And now we want to see the fact that it stabilizes, that after oscillating for a while, exactly at n equals 2m, they get a fixed sign. And now we need to consider a tricky region, n of order m. This is the coefficient being of order the central charge, because we want to look at the point n equals 2 mod n. And so we take this limit, large N and M, and neglect other things which are small relative to these, and we find approximate forms for these Fs. And what you can see now is that they don't actually scale like M anymore, because N is the same size as M. So M squared and M squared in numerator and denominator. The best you can say is that these numbers are greater than 240. But being greater than 240 is just not a parametric bound. It's just a numerical value. It gives you some hope. Expansion in powers of 1 over 240 might not be a bad thing, but it's hardly guaranteed. But anyway, we go ahead and bravely make it. We also notice that this has a sign. When n is below 2m, this is negative. When n is above 2m, this is positive. So this is a very welcome sign. Sorry, that was a pun on the word sign. Which was not okay. Now, you may think that at n equals 2m, this diverges. That's only because we dropped a finite piece in the limit of large N and M. But if n is equal to 2m, we can't drop that. And this is that piece, where j is a small number. So we collect everything and we get this kind of result. Yeah.
When n is less than n,
yeah.
2m.
Yeah.
When n is less than 2m, then the alternation is not seen from this.
It is seen. It's right here. Because look at this line. The an is the product of these f factors from p equals 1 to n, and every one of them is negative when n is less than 2m, because p is less than n. So p is also less than 2m. So each of these factors is negative. So the alternation is seen. It is raised to there are n factors. So depending on the odd or even n, you get minus or plus. Exactly at a to m, you have odd number of minus signs and one more. That's the wrong light. Yeah. Put on other lights, Bharat. You get one minus sign and one odd number of minus signs. The whole thing is plus. Okay, so A to M is positive. This is the identity character with M positive. This is good. And finally, for N becoming a little larger than 2M, still within our approximation, this is negative, and these terms are all positive because now P's are greater than 2M. So the whole thing is positive forever. So now we're actually done. So this was a cause for great celebration until we realized that this approximation is invalid. And I'll just tell you that in a minute. Before doing that, in this approximation, we can ask, how does A to M scale with M? And we found a beautiful result that you can just take that formula on the previous page and just estimate it for very large M, and it grows as e to the 12.19 M. And then we looked at all the examples we knew and extrapolated just assumed an exponential of M, and we got 12.13, which is great. So we thought, wow, this approximation is great. Well, no, because this approximation where n is of order m is not as good as the other approximations I made, for the reason that f is only large in the sense of 240, but not large in the sense of any parameter. And by doing more numerics, we realized that the terms we have neglected individually can be opposite in sign and dominate the leading term individually. But we still expect that when summed suitably, they will still give the same sign. So we tried. So now I won't go into details. We argued that some subset of the subleading terms can be summed and they exponentiate. Once they exponentiate, since it's a real number, it can't be negative. And we are back to our original prediction, but with a small correction. And from 12.19, we get 12.14 M, including these, where the correct answer is 12.13, which is great. But unfortunately, when we do this for the non-identity character, it doesn't work as well. In the non-identity character, the actual growth is more like e to the 9m, but our estimate still gives something of this order. So it's correct, I mean, roughly, but it's a poorer. So this is sort of what I wanted to summarize here. We also gave an inductive proof, which is rigorous and doesn't involve approximation, which just says assume the alternation up to this point, prove that it keeps alternating up to that point, or assume it's positive after this point, prove that it keeps remaining positive. And once the induction works, then, if this is true for a few m's, it's true for all m's. So that works well. So that's what we know. So I'll conclude now. I'm just going to once more show you something, and I don't need to go to all this. Here is a sum of 3 different quasi-characters, and now you see why we did this problem at all. Now there are 2 integers. So I've added these 3 quasi-characters with arbitrary integers n1 and n2. And here you find as before, that N1 is greater than 245. But you also find L is 12, by the way. We've added 3 different terms, so L has to jump to 6 and then 12. But we also find that N2 is bounded above and below. So we are getting something like what I might call a character hadron. It's bounded by, integers bounded by planes. And it has a peculiar shape. Now, the funny thing is, these requirements are only for the up to order Q squared. But they have to be satisfied in the subsequent term. We could tighten these bounds, but we shouldn't have zero overlap between the bounds from higher terms and lower. And this is why we wanted to know the growth of the negative terms and the terms near that crossover point, so that we can do the linear combinations and predict when admissible characters exist. But we do have one example. And there's one example where we can actually find a CFT. See, it always helps if you can find one CFT that satisfies your bounds to show that the bounds are non-empty. And actually, it turns out when N2 is 3 and N1 is 872, there's a CFT. And that CFT, these values lie within the bounds we found. So it's going well, and that's the end of the discussion. Now, I discussed only the L equals 0 case. The L equals 2 case is a miserable failure. Till 2 weeks ago, we thought it will go the same way. It doesn't go the same way. So we finally decided to put out a paper with only the L equals 0 result, and we are still working on L equals 2. Because the recursion is more complicated, the approximation we tried didn't work well. So it's a very non-trivial problem is all I can say. And for rank 3 quasi-characters, these students and I tried and made some conjectural list. It's clearly not complete. And there are things you can compare with. And that is really everything. Thank you very much. Sorry for going through.
We had a lot of questions, but are there any other quick questions?
Is there some introduction in terms of some ghost theories for this negative?
Good. So Jeff Harvey told me there's a thing called virtual dimension of representations which can be negative. So that is possible. I didn't learn about it, but in this sort of representation theory, they do talk about something called virtual dimensions, and those are negative integers. So it might be that the quasi-characters are virtual dimensions.
Why the mathematician?
Yeah, good. Thank you. Very good question. So they want to exactly solve the problem I posed at the beginning, which we didn't actually, no physicist posed it in that way. Can we classify all rational CFTs of fixed rank? They wanted to do that. That's, in mathematics, you want to do something because it's a beautiful question. And Shelikin's result really sparked them off because he classified all the rank 1 at C equals 24. And we all know that the next value allowed is 32 and it's not classified. And mathematicians took one look and said, we can prove a minimum lower bound of 1 billion and we are not going to look at that problem ever again. So that's over. Actually, there are some things which I can tell you privately. So then they turned to the higher rank case. And then some people, Mason, Nagatomo, Sakai, these are some of the names. We got nice mails from them. Mason actually, and these 3 authors wrote a beautiful paper. I'm calling it that because it has our names in the title. And it's like 20 years after our paper. And it starts by saying that our paper is very ahead of its time. And which, from the mathematics literature point of view, it's true. They didn't get to this problem. So very gratifying and all that. And so it's a classification problem. There's people work on how to classify all n equals 2 superconformal field theories. That's considered an obviously more important problem. I'm not sure why, because the standard model isn't going to make use of all of those theories or any of those theories. It's again a classification problem. So I mean, it's just that this particular one has not seen a kind of very widespread interest, but it seems that because of mathematicians' input, it's more interesting now than it used to be.
Is related to 2 dimensions.
Yes. Good. So in higher dimensions, of course, there's no concept of rational CFTs, but the problem of classifying 4-dimensional n equals 2 supersymmetric CFTs is probably the closest in doability to this, in the sense that a lot is known, but most things are still unknown. It's also beautiful, and that problem has relations to this problem, which Ramesh and I have been discussing for the last few days. through something called the Schur operator to vertex operator algebra connection, which is due to, I guess, Beam, Rastelli, Vafa, and Cecotti and company.
Why do we expect the quasi-characters which virtual dimensions to come up to an admissible?
We don't expect. We show that it can happen, and we show that all can be obtained in this way. Therefore, this is one way of constructing all admissible characters.
But mathematically,
No, again, I think this would depend on mathematicians getting involved in this problem. To date, I'll say honestly, there's literally no sign that any mathematician cares about L being greater than 0. In fact, they rigged up a condition called the non-zero Wronskian condition, which they embed in their list of, every mathematical statement has a lot of conditions. Non-zero Wronskian is put somewhere in the middle, and it means L is 0. Because if the Wronskian has zeros, then L is non-zero, right? The Wronskian is the denominator which creates the pole. So everywhere non-zero Wronskian is their condition. That just means L is 0, and then they don't do anything with any other L. It's very frustrating. One exception, the topological quantum computing community actually did a very beautiful paper on L equals 0, 2, and 4. And they found a new theory with L equals 4, which we had found probably that, we had missed, I think. I don't remember. Or maybe our paper was after this. I don't remember that also. In 2016, we certainly missed it. So they wrote an entire paper about one theory with L equals 4 and central charge 33.
Is there some application to quantum computing?
So they think, a few people think so. So this topological quantum computing community, there's a guy called Zhenghan Wang at Microsoft Research Station in California, and he works on TFT and CFT and anion physics, and he got interested briefly in this problem, and then I think was no longer interested. So that was a period when maybe they thought it might be useful for it, because these are theories of non-abelian anyons. So you could say that they are interesting in principle. The theories of non-abelian anyons is just a fact. And if you ask what are all the theories of, now the question is whether you need to know only the TFT or the CFT. If the topological field theory is enough, then that's the MTC and that's classified in rank 2, 3, 4. If you want to know the actual CFT, then we are the people doing that. But then it's not clear to me the anion community wants to know that. We can discuss this. I don't know the anion physics well enough to understand if this is needed or not needed.
What's the extra ingredient? The modular S matrix?
No, modular S matrix is part of the TFT also. The extra ingredient is the actual dynamics of a CFT. So it actually has fields that vary on space and which have correlation functions. TFT doesn't really have correlation functions in that sense. I mean, it has, but it abstracts some matrices out of those correlations, the F and B matrices. But the actual correlation functions are different for every CFT. Structure constants are different.
There are no more questions. Thanks, Oliver.
Thank you for staying this long.
Thank you for your I got lost the last 10, 15 minutes.
It was a little...
No, it was very nice. I got, yeah, you will stand. Thank you.
I wanted to ask you the last time you were lost.
Nice person. Sorry, I missed the first few days.
That was just a reaction to stuff for this meeting. Okay, thanks for coming.
Of course.
Yeah. I'd like to know from you if you know something about this anion world, what they are interested in. It would be very nice to know.
Yeah,
So
I only know a little bit from the chance signals. But this angle, I don't.
I guess what I can do, if you have a little time, I can show you a paper of these anion people classifying CFTs like I did here.
Right.
And let's try to understand from that paper like why they are doing it. But they are not doing it as mathematicians. They are, at least one of them is a TF, is the anion person. The other one is probably a mathematician.
I see.
So why that guy was interested at all? There's some preamble of the paper which I didn't probably get what they were saying. So we can just see. It would be nice to just know, just culturally. Great. Okay.
Okay, so, some deep observation. We have a two-character you satisfies this, modular, images. Suppose I divide by the product of the characters.
Yeah.
Then I'll get I inverse. So it is, shuffled. This also has a Q expansion with the leading the exponent and so on. So this satisfies the symmetric flexibility of modular invariance in.
What happens to rho if I do this equation?
Let's see, yeah. We do it.
I think it's a little more hard.
I0 is like I0 prime.
Yeah.
It's rho 0 0 0.
Good.
Minus 1 0. So if I divide,
Yes.
I get I1 equals
Prime.
Prime.
Yeah.
It's rho 0 0 I1 inverse. 0 0 1 I0 inverse. And then
What have you divided by? Divided by
1 over. Oh, you're saying the
Chi0, Chi1 is not in this.
not in oh yeah, I see.
That is the problem, but you might still be able to do something.
I was thinking about it more in the more general case where I divide the product of all characters.
This is the product of all characters, Chi0, Chi1. But then Chi0 prime, Chi1 prime. So it's an interesting idea. Question is, can we take this equation and divide by the product of all characters to get some modular transformation for the inverse of it?
Yeah.
But we don't, as what he's writing isn't literally true, because here we want to divide by Chi0 prime, Chi1 prime. That's
Right.
After modular transformation. Here we want to divide by Chi0, Chi1. So, but Chi0 prime, Chi1 prime product is not the same as Chi0, Chi1 product, right?
Okay, these are just some modular transformed.
Yeah.
These on the left side are the
Alright.
evaluated on top.
Fine.
No, the products are not the same, right?
Yeah,
The
products are
partition function is the same.
Yeah,
Right, but they don't transform. I mean, there's no nice transformation on it.
actually you can do it even. Chi0, Chi1 will go to a bilinear form in Chi0, Chi1, but that will have terms like Chi0 squared, Chi1 squared, and Chi0, Chi1. Right,
Right. So it's not like a.
It's not just
Right.
Chi0. Yeah, it's not like a wedding. Like, yeah, if it was somehow anti-symmetrized, that might happen. There might still be something in this. It's interesting.
I was just looking at the Q expansion. So 1 over a Q expansion also is
the
a
Q
valid Q
expansion.
expansion.
Yeah.
It's trying to engineer something new down there. Are there MLTs for bounded subgroups of it?
Yes.
Fundamental domain becomes larger.
There are. I think Jeff has.
Something